Okay, today's class we're going to look at some of the science skills that you need to feel comfortable in a grade 11 or 12 chemistry classroom. The first thing I want to look at is scientific notation. Scientific notation uses powers of 10 to describe very large and very small numbers. And the basic rule you have to remember is that each time you move the decimal place, the power of 10, if you move it to the left, the power of 10 goes up. If you move the decimal to the right in a number, then the power of 10 goes down. So here are a couple of examples. You take the number 5,280 and you want to turn it into scientific notation. In scientific notation, there is always one number before the decimal and the rest of the numbers after the decimal. So to turn 5,280 into scientific notation, you have to move the decimal over 3 spaces. And in doing so, it makes you have to write times 10 to the 3 to maintain the same value. For the number 52,800, which is 10 times bigger than 5,280, you have to move the decimal over 4 places to be able to get 5.28. And then, of course, you have to write times 10 to the 4 to maintain the same value. 5,280,000 comes up to 5.28 times 10 to the 6. And if you move the decimal the other way, if you make a very small number, 0 with 0.5 zeros, 528, if you want to write that as scientific notation, you have to move the decimal 6 spaces to the right. And to write that as scientific notation, you would add times 10 to the minus 6. So the fact that I've moved the decimal place 6 places, 6 spots, makes me have to put negative 6 as the exponent. To practice using exponential notation, it's good to be able to convert numbers to scientific notation. And then, of course, knowing your times tables helps a lot. Let's start with the number 1,230,000. The decimal place is here, so we're going to jump it over 6 places, 3, 6. And so that means that our power is times 10 to the 6. For the number 0.00571, we're going to move the decimal place 3 times, giving us 5.71, and the power becomes 10 to the minus 3. This multiplication is 1.2 times 10 to the power of 3 times 1.2 times 10 to the power of 3. If you recognize that 12 times 12 is 144, you can also see that 1.2 times 1.2 will give you 1.44. And then when you multiply two exponents, the rule of exponents says that you add, if they have the same base, you can add the exponents. So 10 to the 3 times 10 to the 3 gives you 10 to the 6. So our final answer is 1.44 times 10 to the 6th. Here we have 7 times 10 to the 5 times 8 times 10 to the 6th. Multiply the numbers first. 7 times 8 gives you 56. But I wrote 5.6 here. I'll show you how I did that. Maybe I should show you the intermediate step. 56 times 10, add the powers, you get 10 to the 11. But to get true scientific notation, you want one number before the decimal place. So I'm going to move the decimal place over by 1, giving me 5.60 times 10 to the 12. Raise the power by 1. In this case, we have 3.0 times 10 to the 4. The decimal place is over here, and if we bring it all the way over here, we've moved it 4 places, so it becomes times 10 to the minus 4. Same thing for the decimal place over here. We move it over 4 places, it gives us 10 to the minus 4 again. 3 by 5 gives us 15 times 10 to the minus 8. And when we move the decimal place to the right, we raise the value of the number by 1. It gives you 1.5 times 10 to the minus 7. The power of scientific notation is much more evident when the numbers are so large they become inconvenient to write. For example, in chemistry, the number of atoms in 12 grams of carbon is 602 sextillion, which is 6.02 times 10 to the 23 atoms. So if you have to write that number out, it would be very inconvenient. Another skill that we want to look at is the transposition of variables. Variables are used in calculations to discern the numerical value of unknown quantities in relation to other known ones. So in a classic example, we have density calculations in chemistry that come up fairly frequently. So the symbol used for density is the Greek letter rho. So it looks like a P with an extra long stem. So rho is equal to mass over volume, where m is the mass in grams and the v is equal to volume. And the units of volume can be milliliters, centimeters cubed, or sometimes you see cc, 2-letter c, small lowercase c's. They mean the same thing. A milliliter is equal to a centimeter cubed is equal to a cc. So before solving a mathematical equation, it is important and customary to isolate the variable that is unknown. So I'll give you an abstract equation for an example. If A is equal to BC plus D, solve for C. Well, the first thing you would do is transpose the D. it's added on this side, so we bring it over to the other side, it becomes a subtraction. A minus D is equal to BC is the result. And then if we want to isolate C, here it's multiplied by B. So if we divide B on both sides, the B here disappears, and we get A minus D over B is equal to C. You can use the reverse of bed mass, the order of operations, when you isolate the variables. Now here's a question where we make use of the skills we just learned. The volume of any sphere is 4 over 3 pi r cubed, where r is representative of the radius. The Earth has a diameter of 7,926 miles, with an average density of 5.5 grams per centimeter cubed. How much does the Earth weigh? So we have two pieces of information here. The diameter of the Earth and the average density of the Earth. So we can use the equation of density equals mass over volume, which I've written over here, solve for mass, and when we plug in the numbers, we'll be able to calculate the mass of the Earth. Before we do this, we have to find out the proper units to plug into the equation. We're going to use units of grams for mass, and for the volume we're going to use centimeters cubed, because the density is stated in grams per centimeter cubed. You have to have units that equate so that they can cancel out. So the first step is to turn 7,926 miles into centimeters. So find the diameter of the Earth in centimeters. We need 3 conversion factors to do that. 1 mile equals 5,280 feet, 1 foot equals 12 inches, and 1 inch equals 2.54 centimeters. So the first step is to develop a conversion factor from miles to feet, where miles can be canceled out. When you want to cancel out a variable, you have to put them in opposite sides of the division sign. So if one's in the numerator, the thing you're canceling it out with has to be in the denominator. So we want to cancel out miles. Miles here is in the numerator, so we have to put miles in the denominator. So the conversion factor is 5,280 feet per mile. If you were to write it upside down, putting 1 mile per 5,280 feet, you'll get the wrong answer. Because mathematically, it makes no sense. You can't cancel miles with miles. You would get an answer with it miles squared to the foot, and that's not a useful quantity. After you've canceled miles, you have the diameter of the Earth in feet. Now you want to cancel feet, and we know that the conversion factor from feet to inches is 1 foot per 12 inches. So you're going to put inches on top, feet on the bottom, so that feet can cancel. The same idea with centimeters per inch. And the final answer, with everything canceled, gives you the diameter of the Earth in centimeters. The diameter of the Earth is twice the radius, so we're going to divide by 2 to find the radius. That's what we did here. We then plug in the value of radius into the equation for the volume of a sphere. 4 over 3 pi times the radius to the power of 3. Remember that when you raise to the power of 3, you not only apply to the number, but also to the unit. So the answer becomes 4 over 3 pi times this number, centimeters cubed. Here's the volume of the Earth in centimeters cubed. When you multiply by 4 over 3 pi, you get this number, and then we can plug this number, which is the volume of the Earth. Sorry, the volume of the Earth is not this number. This is the volume of the Earth. After you multiply by 4 over 3 pi, you get the volume of the Earth. Then you take this number, put it into the equation which we've isolated for mass, times 5.5 grams per centimeter cubed. The centimeters cubed cancel, and you get the mass of the Earth in grams. Then from the mass of the Earth in grams, we've converted it to kilograms by dividing by 1,000. Grams cancel, and you see that the answer is going to be in kilograms. And then if we want to convert from kilograms to tons, we know that there's 1,000 kilograms per ton. Final answer in the mass of the Earth in tons is 6.0 times 10 to the 21. Now you notice I had a bunch of numbers here, but I can't really report to that level of accuracy, because in my question I only had 2 significant figures. So I have to limit myself to giving an answer with only 2 significant figures. So if you round this off to 2 sig figs, you get 6. 6.0 times 10 to the 21 tons. Any questions?